Good afternoon and welcome at the Tech at Lunch organized by Flanders Make. This is the third session out of a series of 5 focusing on energy cost reduction. My name is Ted Ooivaar. I am a technology domain lead and senior research engineer at Flanders Make. And today I will talk about upgrades of legacy machines to enable supervisory energy control. Before we start, I want to explain you some guidelines. First of all microphones and cameras will remain muted throughout the presentation, but questions can be asked during or in the Q&A chat box during the presentation, and these will be answered at the end of the presentation. We will record the presentation and this will be shared afterwards to all of you. Maybe you recognize it. You're working for a company where you make use of machines that are maybe 10, 20, 30 years old. These machines have not yet reached their end of their useful life, but they also do not fully meet the current modern standards if it comes to energy efficiency or sensors or other functionalities. So at some point, the question might come up, do you upgrade the machine or do you replace it? Now, in the next 20 minutes, I would like to show you that in some cases, upgrading an outdated machine is relevant and might be a good option for your case. First of all, it could be financially, could be interesting. Also from a reliability point of view, it could be useful to upgrade the machine. Something new doesn't mean that it is always better. From a training point of view, operators are used to use the machine. Also from a placement point of view, sometimes systems and machine are deeply integrated in a building, so that doesn't allow them to be replaced easily. Environmentally, obviously, and not to be forgotten is the reduction potential to reduce the energy consumption. But if it comes to machine upgrading, there are a couple of challenges. And the first and the main challenge is, what is the business case? So what are the costs and how do you quantify the benefits? A second challenge is what to upgrade. Do you upgrade the electrical parts, the mechanical parts, or do you do it together? There are a lot of technologies available on the market, and it's often not that easy to select the right technology for your application. And finally, how to implement it? How do you connect the old with the new? And how do you avoid that your current production, for example, is affected by the upgrade? So if we look to machine upgrading, there are different types of transformations. First of all, electrical transformation. That is when you talk, for example, about upgrading a control unit, or if you want to change to field bus communication. A second type of transformation are the mechanical transformations. It's more an upgrade to replace worn parts or even changing actuators. A third type of transformation are the digital transformations. This is where data and connectivity basically comes together. And often there we use data analytics tools such as machine learning and deep learning to get an insight in the operation, but also to improve the effectiveness and the efficiency of a machine or a system. And finally, the conformity transformation. That's basically a transformation to make sure that your machine complies to the latest standards in terms of machine safety. In the remainder of this presentation, I will mainly focus on the digital transformation. And that's what I mean with machine upgrading 4.0. How do we bring this to practice? Well, therefore, I would like to show you and introduce you to a use case that we have worked on within Flanders Make. Within Flanders Make, at one of our facilities in Lommel, we have a compressed air network installed. This network was installed about 20 years ago, and we use it basically to provide compressed air to different facilities that we use for mainly experimental testing. We have climate chambers where we use the compressed air, for example, to regulate the humidity in the climate chambers. The compressed air is also used in other equipment, smaller equipment throughout our facilities. So this system was purchased and installed 20 years ago. And over the years, there were several issues reported. We had quality issues. Sometimes there were particles in the compressed air. But also sometimes we had maintenance issues. The compressor broke down, filters were polluted. So this all leads to an inefficient operation and also unwanted downtime for the end users. So the question that we asked ourselves was, can a gradual upgrade of this system improve the overall efficiency, energy efficiency of the system? Where do you start basically with that? The starting point of such an upgrade is a proper cost-benefit analysis. There are different tools available to do this, from very simple like return on investment analysis to more elaborate life cycle costing or total cost of ownership analysis. A key thing, however, is that a proper cost-benefit analysis requires time. The more accurate data you have, the better analysis you can make, the better decisions you can take in the end. But also don't forget there the hidden costs, the costs that for example, for documentation or additional inspections, or that is something that's often forgotten. A good thing or easy thing is that the majority of the costs are often determined by only like a few items. Besides that, a proper cost-benefit analysis requires commitment. It requires commitment through employees throughout the different layers of the organization. Someone who was, let's say, involved in the purchase, for example, who maybe knows still what the initial costs were, and that is something that you needed to be taken into account. So what does it mean for our use case here? So we defined basically three main cost drivers. First of all, the purchase cost. It was quite easy for us. We could trace down some invoices. That was easy. It became already a little bit more challenging when we moved to the maintenance cost. We had a few logbooks. We could see when the compressor was repaired. But also, we had to talk to the facility manager who was involved in several inspections. And this is also costs that you need to take into account. And finally, also we had a few breakdowns, and during those breakdowns, a small replacement compressor was purchased or was used. However, the big unknown in the whole cost-benefit analysis was the operation, so the energy cost. So we didn't know exactly how often the compressor was switching on and off. So basically, we had insufficient data to come to an accurate analysis of the overall costs, and therefore also the benefits. So how did we approach it? So how did we determine the best upgrade scenario for our case? So we had some of the data was coming from the expertise. We were talking to the facility manager. We had some historical data, but the big unknown was the operational data. We didn't know how often it was switching on, and also how much what the consumption was in the end. And this is an important input that you need to estimate, or to get a total overview of the cost-benefit analysis and to determine the best upgrade scenario for your specific case. So what we did was, in a first version of the upgrade, we installed additional sensors that allowed us to get an actual view on the consumption and usage. What we did, so here you see a detailed overview of the full layout of the hardware layout of the compressed air network. On the one hand, you see the compressor chamber, you see the compressed air network in the bottom, and there are different end users throughout the network. So we installed current and voltage sensors to measure the power consumption of the compressor. But we also installed pressure, temperature, and flow sensors throughout the network and close to the end user to see exactly what were the main users in the network. The data that we measured here was then connected to a software framework. And the software framework consisted of several elements. The sensor data was stored in a so-called influx database that was a starting point for different services, such as anomaly detection or other services. This was managed and orchestrated by a Node-RED software environment, which is a low-code programming environment that allows you to easily set alarms and set thresholds. Then this data was also visualized. You see here an example that allowed us to get insights in the usage of compressed air by the different end users from the last day, the last week, the last month. For example, here on the left, you see an illustration from last year where overall we saw a quite high idle consumption, and then every now and then the consumption increased. This was mainly due to the operation of the climate chambers. So we were running for a couple of days during an experiment. But what did we learn from this first upgrade? Well, first of all, we saw that the energy consumption was clearly like a major cost. It was almost about 70% of the overall cost of our compressed air network. Besides that, we saw that we had a quite high idle consumption, partly due to leakages in the network, but it came down to almost 10,000 euros a year. And this was an estimate based on energy prices from 2021. If you could translate that to the current energy prices, you can imagine that these costs are significantly higher. Besides the high idle consumption, we also saw that we had clearly alternating periods of high and low demands of compressed air. We couldn't just switch off the compressor because some of the infrastructure always needed to be kept pressurized. But this analysis was for us the starting point to think about what could we do in a second upgrade. So besides mitigating leakages, we thought we came to 3 potential upgrades. So what will happen if we don't do anything? So no upgrades. What will happen if we change the pressure presets of the compressor based on the consumption and the usage and the activity of the end users? And finally, what would happen if we just add a small compressor to account for the small daily usage of compressed air? So we compared these 3 scenarios using a cost-benefit analysis tool that we made, where we also included an analysis of the worst case and the best case. And this is important because of a lot of numbers are rather uncertain. So if we make that comparison, here you can see for the 3 scenarios, we made a projection up to 2025 of the annual cost. We could see that, okay, if we don't do an upgrade, we reach an annual cost of about 19,000 euros a year. But that with the 2 other scenarios, we reach a significant reduction in the costs of running this full network. The biggest reduction will be obtained by adding a small compressor, but this requires also an investment of buying a small compressor. So that's why we decided in this case to focus on the second scenario. So it delivered us a relatively large return for a rather small investment in the end. So basically what we did was, by including the sensors into the network, we got a better estimate or insight in the operation of the compressed air network that allowed us to come up with a more accurate cost-benefit analysis. And based on that, we could define what upgrade scenario was the best in our case. So in the second upgrade, we implemented this active pressure preset solution. The initial situation there was that the compressor was always running at a high pressure preset, which led to high leakage losses. And also we had the alternating periods of high and low demands. So we implemented a control algorithm that basically adjusted the pressure presets here between 8 bars and around 7 bars, depending on the needs and the demands of the end users. We could implement this rather easily because the system allowed us to have an external interface where we could set the different presets. So what did it bring us in the end? Well, here you see an analysis, an overview of how often the compressor would run in the high demand and a low demand state. Based on analysis over a period of 1 year, we estimated that in about 83% of the time, the compressor would be able to run in a lower pressure preset, which would lead to lower leakage losses. So to put this really into numbers, by performing the gradual upgrade, we could reduce the energy consumption. First of all, by mitigating leakages, we could reduce it by between 11 and 50%. But by implementing the active pressure preset, based on the activities of the end users, we further reduce it to between 13 and 80%, which is significant if you consider particularly the current energy prices. Coming to the end of my talk, a few key takeaways. So a good machine upgrade comes and starts with a proper cost-benefit analysis. But a cost-benefit analysis often is very uncertain. The numbers are uncertain. So this requires a good commitment from people like different layers of the organization, the people that were, for example, involved in the purchase. And besides that, it is important to do not forget the hidden costs. And at the final point, like what I showed here in this talk is following a gradual digital upgrade approach can help you to rather quickly get a good insight in the operation and usage of a machine or system. It can identify large cost drivers and opportunities for improvement. And in this case, like it could show you what the energy reduction it could bring. So in my talk, I mainly focused on digital upgrades and how a digital upgrades could bring benefits in terms of energy consumption. If you're interested in some of the other upgrade scenarios, a mechanical upgrade, electrical upgrade, or conformity upgrade, I would highly recommend you to download and read the white paper that we wrote last year together with the company Vintiv. Besides that, if you have specific questions related to machine upgrading or how you further can reduce energy consumption in your machine or system, Flanders Make is an organization that can help you with this. So feel free to reach out to us. My contact details are written here on the slide. And before we move on to the Q&A session, I would like to pay attention to the following talk that would take place on the 5th of December with the title Energy and Resource Efficiency of Discrete Manufacturing Processes. We would recommend you to subscribe to this session. And with that, I think the floor is open to the Q&A session.
Okay, thank you, Ted, for the presentation, which seems to be a very clear explanation because there are not many questions. We have one question so far, which is, would you recommend to roll out sensors more broadly, or would you only focus for machines or equipment where you identified possible business cases?
I would start from the business case for sure. Yeah, that's for sure. That's the starting point. So it doesn't make sense to do a very high investment for something for a gain that yeah, it's maybe is negligible. So I would first identify what are the hotspots, what are the potential key, let's say, components or machines or systems where you think that's where an added value can be observed or can be obtained. And focus on that. Start small before rolling it out to a full plant. Yeah.
Okay, thank you. There are no more questions so far, so I just suggest we wait like 30 seconds to see if there are more questions coming up. And otherwise, we can wrap up this session, but we'll just give it a few seconds. Okay, so I guess there are no more questions. If you, however, have more questions or you tuned in a little bit later, you can still ask your questions and we will collect them and try to reply individually. So don't hesitate to still ask questions in the Q&A. So now I leave the floor to Ted to close the session.
Good. I would like to thank all the participants to listen to the story, and we hope to see you in the next session that will take place on the 5th of December.